Okay, we're going to look at a few curves here to graph by using some tools that we've discussed this week. We're going to look at, the horizontal asymptotes, which are limits at infinity, intervals of increasing, decreasing, and intervals of concavity. So we're going to look at these items here to try to sketch these curves. And so I have included the curve here as well, so you guys know what to expect. So we'll use the analysis and determine how this curve behaves here. So the first thing we're going to do here is we're going to find where this curve increases and decreases, and in fact find relative max and relative mins. And in order to do that, we need to actually do sine analysis on the first derivative. So for the first part, intervals of increasing, decreasing. So if my function is x over x squared plus 1, we're going to have to take the derivative. So as you can see, we're going to have to use quotient rule. Okay. So we get these derivatives here. And we'll use some algebra. So combining like terms in the numerator looks like it gives us 1 minus x squared here. Okay, so here's that first derivative now, and we have to use sine analysis. So remember about sine analysis, we want to find where the numerator is 0. That gives you the derivative being 0. We're going to find the critical values. All right, so we're going to look for those critical values, CV. And the numerator now equals 0. So it looks like we have 2 critical values, but we got to make sure. We got to make sure that these values are in the domain of the function. So they're not critical values yet until we know they're in the domain. And this function is defined for all real numbers. If we look at this function here, y is x over x squared plus 1. That's defined for every real number. In fact, the denominator here is never 0. Right? Down in the denominator portion, it's never 0. X squared plus 1 cannot be 0. So here's what we're saying. So this is defined for all real numbers. That's in the domain. Now, what that means here is that, yes, these are critical values. So I have positive 1, negative 1 as critical values here. The denominator equal to 0 now. Of x squared plus 1 squared, we set this equal to 0. This is that denominator. We're going to find critical values. We're going to find where the derivative does not exist. Now, this means x squared plus 1 must be 0, and we just got through seeing earlier that this never happens. Right? You'll get complex solutions if we try to solve that. So the denominator doesn't contribute here in any way to the critical values. So the only critical values we have is positive 1 and negative 1. So in sine analysis, since the domain is all real numbers, we're going to check the signs on this first derivative. 0 at -1, and +1 here. Okay. So we have 3 regions here. Region 1, Region 2, Region 3 to test. So we're going to use a test point. -2 is clearly in Region 1. 0 is available in Region 2. And we're going to use 2 as a test point in Region 3. So we're going to perform a sign analysis on that first derivative here. Okay, the first derivative is right here. So here's our first derivative. We want sign analysis on this. So we're going to plug in -2. We're going to test Region 1. So I want to get purple here. Okay, -2 gets placed inside there. So this is 1 minus. Replace x with -2. And ladies and gentlemen, we get 1 minus 4 over 4 plus 1 squared. Now the denominator is actually positive. In fact, it's positive all the time for any real number. That denominator here, down here, the x squared plus 1 is greater than 0 for all x. It's the denominator that's negative, though, because 1 minus 3 up here is or 1 minus 4 is a -3. I gave the answer. So a negative over a positive will give you a negative. So we know region 1 is negative. So this is a negative region for that first derivative. So we're now going to test region 2. So we're just going to replace now the x value with our test point of 0. We're going to plug in 0 now. And when we plug in 0, we get 1 minus 0 squared over 0 squared plus 1 squared. Now the denominator is always positive. And in this case, the numerator is just 1, which is positive. So a positive over a positive, this is going to be 1 over 1, which is 1. A positive 1. Region 2 is positive. There we go. We need a test point for region 3 now. 2. So when we test region 3, we get 1 minus 2 squared in the numerator, which is a 4. And we get, looks like 2 squared plus 1, 4, that's 5. So it's going to be -3 over 5, it looks like, 5 squared, which is 25. And so, ladies and gentlemen, that's negative. We don't care about the answer. Region 3 is negative. Okay. So in region 1, we have a decreasing slope there. The function is decreasing on region 1. It is increasing on region 2, and it is decreasing here on region 3. So we have some important information here. I'm going to move this out of the way. And so we look at this curve here, and we have some conclusions now. I'm going to get rid of all the scratch work. What we know essentially about the curve is that this curve is increasing. So let's draw our conclusions. F is increasing on 2 intervals from -infinity up to -1, union 1 to infinity. Oops. Decreasing on 2 intervals. This is what I'm looking at. Okay, apologize for that. It's negative in this interval. It's negative in this interval. It's increasing only in the middle there. So we can say f is increasing on the interval from -1 to 1 here. Now, since we have the change from a decreasing function to an increasing function, we're staying in a valley there. So the function has a relative min at -1. This is the value you're looking for. So at f of -1, you have a relative min, and then you're talking about a hill here. When x is +1, maybe we should change the color. -1, +1. At +1, though, you're on a hill. So that's a relative max. We just need to know what those values are. And we have to plug them into the curve, the original curve, -1 and +1. So if I go back to this original curve here, right? If we plug -1 in first to x, that y value is -1 over -1 squared plus 1. So the y value will be a -1/2. Okay, so it's -1/2. The x value, or the x value now is 1, the relative maximum value, plug in 1, plug in a +1 now. And when you plug in a +1, we get +1/2. Okay. So +1/2, the relative max. This is going to be important details, because you're essentially looking at the graph of the curve right in here. This is really how the curve looks. You know, that information. So if you said, well, how do we start to sketch this? I'm going to bring in Cartesian coordinates. And this is kind of not going to be to scale here, okay? But at -1 and +1, we have the relative min, relative max. So if I go and say maybe 1, 2, 3, 4. Let's not do it to scale. 1, 2, 3, 4. This is where we have those x values for relative min, relative max. But the relative min at -1 is -1/2. So if each one of these lines, well, every 2 lines is 1. So this will be -1, -2, +1, +2, -1, 1/2 would be right in here. And then +1, 1/2 would be here, since this is 1 and 2 and -1 and -2. So we have these locations here. We know the curve to the left of that value, to the left of -1, is a decreasing curve here. So I'm going to draw a straight line. Let's draw a decreasing line to mimic what's going on in quadrant 1 there, because you're decreasing from -infinity up to -1, and then you're increasing from -1 to +1. So I'm going to draw a straight line here. Okay, there's my increasing slope, and then I'm decreasing again. You know, this is kind of a rough kind of sketch of this so far. But in my mind, this is a lot of information just in that first derivative. Okay, and so you might say, well, what about the second derivative now? We got the first derivative. How does this behave in terms of concavity, right? Let's get that first derivative. We now need the second derivative for this function. Okay, so let's get the second derivative. We got to find concavity now, the intervals of concavity. And so again, we have the quotient rule, and I think there's no way around this quotient rule. So we're going to square that denominator, and now it's to the fourth power. X squared plus 1 squared up here. Derivative 1 minus x squared times 1 minus x squared derivative of x squared plus 1 squared. So let's be careful here. Okay, so we want to double check to make sure everything's okay. This derivative is minus 2x. We're going to have to use chain rule here. 2 x squared plus 1 times the derivative of x squared plus 1, which is 2x. This is chain rule, so there's going to be some algebra here. Now I'll simplify that. Okay. What I think I'm going to try to do in this numerator, I see a common term. X squared plus 1 squared and x squared plus 1. I'm going to do just a factorization, factor out the greatest common factor of an x squared plus 1 here. That'll leave me with a single x squared plus 1 times that minus 2x minus a 1 minus x squared times a 4x up here. And you have that x squared plus 1 to the fourth power here. And it'll disappear in the numerator, but we're now going to distribute here. So we're going to distribute here, and we're going to distribute here. But this will cancel. This is now 3. Okay. So we end up with negative 2x cubed minus 2x. And I'm going to leave this term here. 4x minus 4x cubed here. Let's double check. Okay. I'm going to get rid of the parentheses, which really means change my signs here. And so, ladies and gentlemen, let's simplify the numerator. Looks like we're going to have 2x cubed, cancel those terms, minus 6x. Now we're out of some space, so what I'm going to do is have some scratch paper. Okay, scratch paper here. Second derivative, so factor out the greatest common factor of a 2x. And then that's x squared minus 3 in the numerator. over x squared plus 1 cube. So let's double check. Okay. This is my second derivative now. So sign analysis on the second derivative, again, set the numerator equal to 0, solve for x, find where that second derivative is 0. So 2x times x squared minus 3 equals 0. Set the denominator equal to 0. X squared plus 1 to the third power. So the denominator and the numerator. All right. Two x is 0. X squared minus 3 is 0 by the zero product rule. This means x is 0. X squared is 3. X is plus or minus the square root of 3. So these are not critical values, ladies and gentlemen, but they are values where that second derivative equals 0 here. And then here we have x squared plus 1 is 0 if we take the cube root of both sides. And then we know this never happens. Right? We take the cube root of both sides. If you said, what did we just do? And then we know x squared plus 1 could never be 0. That gives you imaginary solutions here. Okay, so we're on our way. So let's continue with our sign analysis now on our second derivative. I'm glad we have some scratch paper. Minus square root of 3, 0, square root of 3. Second derivative is 0 at these three locations here. So we'll have 4 regions now. And we need test points. So we need to know what the square root of 3 is. The square root of 3 is smaller than the square root of 4, so it's smaller than 2. So we'll use like maybe a negative 3, positive 3, or if you like, a 4. Doesn't matter. Test point. Test point. Right? Square root of 3 is bigger than 1. In fact, square root of 3 is about 1.7, so we're going to use 1 as a test point. 1's a good number, so it's negative 1. Okay, so we do have some good candidates. Now the second derivative here is what we have to test. Now I want to point out that the denominator here is always positive. Right? If I square a number, that makes it positive. If I add 1 and then I'm cubing it, so this is always positive. So that's a good thing to observe because it really just means I get to check the numerator. So this is positive for all x. Only check the numerator. So if I plug in a negative 4 as a test point, we'll get 2 times negative 4. Negative 4 squared minus 3. Negative 8. 16 minus 3. I really don't care about the answer. I just care about the sign. So a negative times a positive, region 1 is negative. Now, we could check the last region since we're using some sort of symmetry, meaning plug in a 4 there, positive 4. This is now positive times a positive, so the last region with the test point of 4 is going to be positive. So I'm just going to do this kind of just to be a little bit quicker. That just means region 2, region 3 need to be tested. Just have to test the numerators because the denominator is always going to be positive. So when we test -1 now, just for the numerator, -1, -1 squared. That's 2 times -1 is -2. Positive 1, 1 minus 3. So it looks like we're going to have -2 times -2. Let's be careful here. -2, yes, positive. So region 2 is positive. Okay, let's test region 3. So when the test point is 1, 2 times 1 is 2. Then 1 squared minus 3 will be a -2. So it's a positive times a negative. Looks like region 3 is negative. So you might say, what does this mean? Well, concave down, concave up, concave down, concave up. And in fact, you change concavity at -3 at 0 and negative square root of 3 at 0 and positive square root of 3. So that means we have some inflection points here. All right, let's answer all of these things here. Let's summarize this. Square root of 3 is about 1.7, by the way, ladies and gentlemen, so you know. So negative 1.7 approximately. And positive 1.7 approximately. So let's give the summary. F is, we'll go with concave up first. Region 2 and region 4. On, let's look at these intervals. Concave up. Let's color the interval. From negative square root of 3 up to 0, positive square root of 3 to infinity. Concave up. Now my function is concave down, and you say which intervals are concave down? Negative second derivative, negative infinity up to negative square root of 3, and then from 0 to positive square root of 3. Negative infinity up to negative square root of 3, then 0 to positive square root of 3. Okay. We have some inflection points. Points where you change concavity. And that happens, remember, it's a point on a curve. So when x is minus square root of 3, the y value, though, is f of minus square root of 3. That's my first inflection point. 0, 0, f is 0. And then the last inflection point happens at the square root of 3 here. So it's the square root of 3 comma f of square root of 3. So I have these 3 inflection points. Now I can go back and try to find, if you say what was the original function. No, the original function. I believe that's x over, what was that original function? X over x squared plus 1. So if I plug in these values now, if I look at minus square root of 3, it looks like I'll have minus square root of 3 over as a numerator. Negative square root of 3 squared will just be 3. 3 plus 1 is 4. 0, we get 0 over 0 squared plus 1, 0 over 1. So that looks like that's going to be 0. This is my inflection point. And with just the square root of 3 in the numerator, square root of 3 in the numerator, and then square root of 3 squared plus 1 is 3 plus 1, which is 4. So we have our inflection points. So we found everything we wanted to find, ladies and gentlemen. All this analysis. Now, if we go back and let's erase this work here. Okay, it's in the video. And I really hate to erase it. Here we go. Just going to put the summaries down there with all the other information. So maybe we'll use just the scratch paper, you know. I guess I could put it right here. Okay. Concavity. Inflection points, minus square root of 3. That's about a 1.7, and then it's a minus square root of 3 over 4. So, I mean, we may want to find here, first of all, before we go that route, we may want to look at the limits now at infinity. Look at the end behavior. So let's kind of get rid of some of this scratch work, and we'll look at the end behavior here. Or we can actually, yeah, maybe we should just use the scratch paper. This end behavior, limits at infinity. All right. Anyway. X over x squared plus 1. So here's my scratch. So here's my function. Now let's look at the check for horizontal asymptotes. Okay, we need to look at the limit as x goes to positive infinity of x over x squared plus 1. And we're going to look at the limit x goes to negative infinity. Okay, two limits. Checking for horizontal asymptotes. So again, we always divide by the variable with the highest power in the denominator. In this case, it's x squared here. Divide by x squared for each term. Limit x goes to infinity. 1 over x squared in the numerator. 1 plus 1 over x squared in the denominator now. So by properties of limits, here's what we know. As x gets big, 1 over x squared goes to 0. So that means the numerator is going to 0 and a portion of the denominator is going to 0, which is 0 over 1 plus 0. 0 over 1, and this limit is 0. There's a finite value. So as x gets big, y goes to 0. In other words, y equal to 0 is a horizontal asymptote. All right. Now notice everything that we just did, we could do the same for x going to negative infinity. So when x goes to negative infinity, we get y going to 0, which means you have that behavior, being as you go to negative infinity, you have the same horizontal asymptote. You don't have two different horizontal asymptotes. So here's our horizontal asymptote, ladies and gentlemen. So it didn't matter if it went to positive infinity or negative infinity, it goes to the same location, y is 0. So let's go back here. Let's double check here. That's the right function. X over x squared. Get rid of some of this scratch work. So when I go look at this picture, this helps me. We know we have a horizontal asymptote of y being 0. So we never cross this line here of y equal to 0, except possibly in the middle, and we do. So that's what this means, because this is a limit at infinity. This is as x goes to infinity. It's not in the middle. It's end behavior. So as x goes to infinity, y goes to 0. As x goes to minus infinity, y goes to 0. So this line that we drew, not to scale, as long as you do an increasing line there, as long as I do a decreasing line here, that's essentially how the curve is behaving here. Okay, now we're going to look at this concavity situation, holding water, not holding water. These inflection points are going to be meaningful for us. At minus square root of 3, that's about 1.7. And minus square root of 3 over 4, ladies and gentlemen. So you're going to divide 1.7 by 4, which is about 0.4. It's negative 0.6. So I'm going to approximate this here. This is what I'm saying. Negative 1.7, negative 0.6. Positive 1.7, positive 0.6. Because square root of 3 is about 1.7. It's just a rough estimate. So negative 1.7, negative 0.6. So if we look at this here, every 4 marks, negative 2, positive 2. So inflection points, negative 1.7, I don't know, negative 0.6, somewhere like in here, and somewhere over here, something like that. So you are concave up. This is going to be, it's negative 1.7, positive 1.7, negative 1.7, positive 1.7. So that 1.7 point here is pretty important. So you're going to be concave up from negative 1.7 to 0. Here is 0. So you are holding water. So let me try to draw holding water in this interval here. Essentially, holding water, ladies and gentlemen. Concave up. And then from 1.7 to infinity. Right? So from negative 1.7 to 0, and then 1.7 to infinity, you're concave up. And that means you're holding water again, something like that. Concave down from negative infinity to negative 1.7, so you're not holding water, so you're kind of going like this, right? But you're still, you're getting close there. Not holding water. And then from 0 to 1.7, concave down. So this is like this, not holding water. So it's a very subtle thing in my picture. This is what they expect you to sketch. And then verify that this is kind of this is the nicer sketch that you are having here. So it kind of looks somewhat the same here. Anyway. That's what they wanted you to do. So I have all the important locations here. This is a rough sketch of this. And anyway, I'm going to let you guys do the evens. I'll do the odds here. I'm going to do number 3 now. Okay, so this is the function for number 3. We'll see how this goes. This is 1 plus 2x squared over 1 plus x squared. But I'm going to go start to do some of the work on the scratch paper. Okay, so 1 plus 2x squared over 1 plus x squared. So let's go to the scratch. Should call that scratch. How's that? Okay, 1 plus 2x squared over 1 plus x squared. We're going to start doing this on our scratch. Maybe we'll just start by finding the horizontal asymptotes. We'll go in the order in which it says. So we'll start that way. Let's look at the limit x goes to infinity. 1 plus 2x squared over 1 plus x squared. Okay. Again, same procedure. Divide by the variable with the highest power in the denominator, which will be an x squared. So for every term, we divide by x squared here. So let's take a look at the limit. Okay, so I'm going to look at it this way. We can look at it as properties limits. You know, we can look at it slightly different than what we did in the past, I guess, or we can say this. Let's do this. Right? As x goes to infinity, we know 1 plus x squared goes to 0. So what that means is this is going to 0. This is going to 0, which means y, which is the function. This whole thing is y. Y is going to 0 plus 2 over 0 plus 1, which is 2 over 1. Y is going to 2. So in other words, y equals 2 is your horizontal asymptote. It's going to be good information. So I'll go back. And number 3, I'm going to draw my conclusion here. Horizontal asymptote, y is 2. And that makes a lot of sense if you look at the picture. That's the line y is 2 here. So it makes a lot of sense. Okay. Let's get that function. Do sine analysis on the first derivative. We have no choice. We got to use quotient rule. 1 plus x squared, derivative 1 plus 2x squared minus 1 plus 2x squared, derivative of 1 plus x squared. It barely fit. Okay, differentiate. 4x, 2x. Okay. Let's do some algebra. We can't factor here, so we just have to use the distributive property. Just double checking the algebra. Notice 4x cubes go away. 4x minus 2x, you're left with just a 2x here. Okay. First derivative. Sine analysis. Let's find the critical values, CV now. We're going to set that numerator equal to 0. So if 2x is 0, that means x is 0. Okay. Is it in the domain of the function? Yeah. Again, ladies and gentlemen, the domain's all real numbers here, because take a look at that. 1 plus x squared will never be 0. In fact, 1 plus x squared is always positive here. I wanted to write that down, but I have no space. I'll write it above. That's always positive. That's going to be good to know for sine analysis. It's also good to know because that means this denominator, when you set it equal to 0, you say 1 plus x squared is 0. We're going to set that denominator equal to 0 like we did the numerator to find critical values. Well, if you take square root of both sides, that means 1 plus x squared has to be the square root of 0, which is 0, and that never happens. So the only critical value we have happens at 0. That's good to know. Okay, the only critical value is at 0, so we're going to have a sine analysis here. First derivative, 0. First derivative is 0. Region 1, region 2. -1 as a test point. +1 as a test point. And we are testing, ladies and gentlemen, the first derivative here. Okay. So plug in the first test point. -1. The bottom here, if you said, what about the bottom? The bottom's always positive. If I square -1, that's +1. And then 1 plus 1 is 2, and square root 2, that's 4, so it's positive. But the numerator is negative because 2 times -1, that's a -2. That's -2 over a positive number down here. And a negative over a positive is negative. So we have a decreasing situation in region 1. Repeat the process. But this time, 2 times 1 is 2, and then the 1 squared is 1. 1 plus 1 is 2. 2 squared, that'll be 4. It's +4. Okay, it's 1/2, but region 1 is positive. So that has meaning here. We are decreasing. We are increasing. And I'm going to copy all of my scratch here for the first derivative. This is sine analysis on that first derivative, right? Negative slope, positive slope. We're going to go back to our summary here. I'm going to put this here. Okay, let's do some conclusions here. this means the function is decreasing on the interval negative infinity up to 0. F is increasing on 0 to infinity. So there we go. You are standing in a valley, so it has a relative min. There's no relative max. It has a relative min, and it's equal to f of 0 here, because it happens at 0. That first derivative is 0 at 0. Unit relative min. So if my input is 0, I go back up here, and you say, what happens if my input is 0? What's y? 1 plus, can't even see that, but we're going to plug in a 0 there. Okay, for x, we plug in a 0. 1 plus 2 times 0 squared, 1 plus 0 squared. So, looks like it's 1 plus 0 over 1 plus 0, which is 1 over 1. 1. And that makes sense because this is that valley that they're talking about. This is 1. Okay, that's a relative min. You're in a valley there. So this is our conclusion here. So we get this just by looking at sign analysis on that first derivative. And, you know, if you said, well, how would that sketch start to look? If you had to sketch this, I'd bring in a sketch. I'd bring in a graph. And we'll see if we can put it. Yeah, it does not like, so you guys know. I'm gonna put it over here because it does not like going on one of those creases. And okay, let's see if we can try to sketch something here. Okay. At 0, we have a relative min of 1. We have a horizontal asymptote of 2, so I guess we can try to do it that way we did earlier, right? Every 4 lines is 1. So you go 1, 2, 3, 4. 1, 1, 2, 3, 4. Okay. Here's 2. So horizontal asymptote, y is 2. And then we have a relative min at 0, which is 1. So it looks like we're here. Okay. Just keep in mind the function's decreasing. So it's decreasing to the left of 0, up to 0. So somehow, when we draw those lines here, this is like the sign analysis picture is what I'm talking about. Because you have a relative min at 1, but you have a horizontal asymptote as well. So you're contained, the curve is contained here. This is like region 1 and region 2 for sign analysis here. So this is kind of a rough sketch when you look at this picture of the graph. Okay, so I just used all of this information right up here with the horizontal asymptote information. That's all I used. Now I have to think of concavity. Where is it concave up, concave down? So I need sign analysis now on the second derivative. And I need, sign analysis on the second derivative, and I think that's in my scratch. Okay. First derivative is here. Sign analysis now on the second derivative. Copy. Let's do that here. Second derivative. Quotient rule again. That's fourth power. 1 plus x squared squared. Derivative of 2x minus 2x. 1 plus x squared squared. Okay, it fit. Let's take our derivatives. Derivative of 2x is 2. This derivative, we're going to use chain rule. Okay, so 2 times 1 plus x squared times the derivative of 1 plus x squared, which is 2x. And again, you get that 4x of 1 plus x squared here. Okay. Let's write down the algebra. 1 plus x squared to the fourth now. 1 plus x squared squared times 2 minus, this is going to be 2x times 4x times 1 plus x squared. Okay. And let's double check. 2x times, this is what I'm saying. And that's 8x squared, by the way. So I'm going to put it here. 2x times that 4x times 1 plus x squared. I'm going to factor out the greatest common factor for the numerator, which is 2, 1 plus x squared to the first power. Taking out the greatest common factor. And that leaves me with a 1 plus x squared now, minus, now let me be careful. 2, 1 plus x squared to the first power leaves a 1 plus x squared, minus a 4x only. 1 plus x squared to the fourth power here. Now, like before, power 3. 2. This would be 1 plus x squared minus, is that minus 4x? No, that's a square. Good. Good. Got to be careful. Everything over 1 plus x squared to the third power. Second derivative is 2, 1 minus 3x squared over 1 plus x squared to the third power. And there you go. Here's the second derivative. So now the sign analysis portion. Set your numerator equal to 0. 2. 1 minus 3 squared equals 0. And then the other situation is 1 plus x squared cubed. Set the denominator equal to 0. One minus 3x squared is 0. Let's solve for x. So 1 is 3x squared. X squared is 1/3. X is plus or minus square root of 1/3. We get to simplify that radical. That's 1 over the square root of 3. Plus or minus square root of 3 over 3. Here's my critical values. Sorry, it's not critical value anymore. We're out of that mode. This is the second derivative. Take the cube root of both sides, ladies and gentlemen, and we get 1 plus x squared equals 0. This never happens. So 1 plus x squared is never 0. So for sign analysis, it's only these two values on the second derivative. Minus square root of 3 over 3. Positive square root of 3 over 3. And this is the second derivative here. Region 1, region 2, region 3. Now, the square root of 3, again, is about 1.7. So 1.7 divided by 3 is approximately 0.5. So just to let you guys know, when I look at this, it's kind of like approximately negative 0.5 and positive 0.5. So I'm just thinking about that. You know, it's really closer to 0.6, but you know. So a test point like -1 is good. A 0 is available. And then a test point like +1, they're in the regions here. So these are my test points. So I'm going about sign analysis on that second derivative with these test points here. But we need the second derivative now. So when we test -1, plug in -1, y double prime becomes, or that portion is 2, 1 minus 3, -1 squared, 1 plus -1 squared to the third power, 2, 1 minus 3 times 1. The denominator is always positive, ladies and gentlemen, so I don't even have to check that. It's 1 plus 1 cubed. Just check the numerator. So this would be 2 times 1 minus 3, or really 2 times -2, so that's negative. So region 1 is negative. Okay, I can do the same again. Right, but we're going to test +1 now. This will be region 3. So remember, the bottom is always positive, so this will be 1 minus 3 times 1 squared. 2 times 1 minus 3, again, 2 times -2. Region 3 is negative. We're going to just test that quickly. That just leaves the test point of 0, and then 0 squared is 0. 3 times 0 is 0. And then you have just 2 times 1. And that's positive. So region 2 is positive here. So this is sign analysis. Now, what this means is you're concave down, concave up, concave down here. And I'm going to copy this. We can put this in our conclusion section here. Write down what that stuff means. Maybe undo. Undo. Write it down here. Yeah, there we go. All right, let's draw some conclusions here. Let's draw the analysis here. So our function is concave down, where the second derivative is negative. And that's from negative infinity up to negative square root of 3 over 3. Union, positive square root of 3 over 3 up to infinity. F is concave up in the middle. Minus square root of 3 over 3 plus square root of 3 over 3. And it looks like, yes, we have some inflection points. Right? We change concavity at these values. So you'll have a pair of inflection points. Minus square root of 3 over 3, f of minus square root of 3 over 3, positive square root of 3 over 3, f of positive square root of 3 over 3. Now your function over here is what you see. One plus 2x squared over 1 plus x squared. Now, if you wanted to kind of give an idea of what these are, right? Minus the square root of 3 over 3 was like 0.5 and 0.6, right? So let me do something like this. I think 1, 2, 3, 4. This is positive 1, negative 1. So, I mean, you can kind of, if you wanted, to find those values. You know, I just want to kind of say this. Let's put this here. If I plug in the square root of 3 over 3 into x squared, right? You get 3 over 9, which is 1/3. So in other words, this is 1 plus 2 times 1/3, which is 2/3. 1 plus 1/3. I can multiply the top by 3 and the bottom by 3. Right? Give you a rough idea. 3 plus 2, yeah, over 3 plus 1, so it's like 5/4. So, and it doesn't matter if it's even negative because you're squaring it. So if you said, is that the same as if you're squaring? Yeah, so this will be 5/4, ladies and gentlemen, for both of them. And 5/4 is 1 and 1/4. So you can plug that in and you get the exact inflection points, 5/4. So here's my point. Like 1/2, 5/4, this is the point here. And I think this is wrong. We want 4 spaces. There we go. 1/2. This is the location of the inflection points approximately. And let me be a little bit more symmetric. Okay. Meaning it's right up here, but then that means this line, you know, yeah. Anyway, something like this. But let's make use of this concavity now, right? This is the halfway mark is what I just did. This is about that. This is undo. That's square root of 3 over 3. This is minus square root of 3 over 3 here, approximately. It's a little bit further away, but. So you're concave down, negative infinity up to that point. So concave down means your curve does not hold water. So let me try to sketch not holding water. It's kind of curved like this, right? Not holding water. And then it changes concavity to the other location where it holds water. So now you're going through this point holding water in the middle. And then you go back to concave down, not holding water. So you don't hold water, something like that. So get rid of this, get rid of that. And you never guess by this graph, but my parents are in fact artists. Okay? But that's kind of a rough sketch of what's going on here, using the tools we studied in calculus. Now, that's pretty much what you see here as well, you know, in this picture here, ladies and gentlemen. So there you go. I'll leave the rest for you guys to do with the evens, and I did include the graph there so you can compare your work with what you're doing. So there you go, ladies and gentlemen. Have a great day. Take care. Stay safe. And we'll see you guys later.